Welcome everybody once more to the official IAU G2 online conference series. As usual, this is about massive stars. And today is my real pleasure to say hola to Angela Adamo. Angela is an Italian astrophysicist, now hosting a position as associate professor at the astronomy department of the University of Stockholm in Sweden, where she is also deputy director of bachelor and master programs. She was awarded her PhD in astronomy at Stockholm University back in 2011, and the title of her thesis was Star Clusters in Blue Compact Galaxies, Evidence for a Near-Infrared Fluxes and Properties of the Starbars. After that, she stayed for a bit more than 3 years as postdoc fellow at the Max Planck Institute for Astronomy in Heidelberg, in Germany, and moved back to Stockholm in 2014, where she stabilized in 2019. Yeah, I've seen in her CV that she has been awarded several research grants and was the winner of the annual prize for distinguished young researchers by the P.L. Lindahl Foundation and the Royal Swedish Academy. And also that she is active member of several international collaborations, including the Venus and Glimpse surveys and the Cosmic Spring collaboration. And since 2021, she's the leader and coordinator of the James Webb Space Telescope FEAST project. And indeed, I've learned that she has been PI or co-investigator of a total of 22 approved proposals to James Webb, so it's amazing. Her main research interests are focused in the study of star formation in local galaxies with the goal of linking small-scale physics to the galactic scale properties. So it's a bit different to the topics that we are normally having in these seminars, but it's great. I'm sure it will be great. And I'm sure she will be showing us very interesting results in these regards in her seminar. So thank you very much once more, Angela, for accepting the invitation of the IAU G2 Commission. And whenever you want, the floor is yours.
Yes, thank you very much, Sergio, for this thorough introduction. And thank you all for joining today. I realized that this is a bit of a step, so we are going to move a bit more farther and overall intermediate scale from the science that you typically do, so looking directly into resolving the stellar population. But actually doing this step backwards allow us to look at the stellar cluster at all stages, from forming into evolving and possibly becoming globular cluster. And therefore we can do kind of a demographic study, so putting into context how stars forming within star cluster then will evolve and actually interact with the galactic scales. So the title is not a typo, the glimpse. You will understand in a little bit what the glimpse is. And essentially the background image that you see here, you are looking directly into the galaxy cluster core of the glimpse survey with the many beautiful arcs. And if you look, all these little red points in these arcs are all star cluster. This is an amazing image of our universe and early galaxies and star cluster within them. So all the work I'm going to present is part of a teamwork, but especially I would like to thank, before I start, Adelaide Clessans. She was a postdoc here until end of last year, and we are continuing working together. And you see that all the results that we have actually achieved is it has been a hard working hours setting by both of us, but Ada has really been doing an excellent job. We feel like we are starting, we are kind of contributing into the field. This field of looking at star cluster high-redshift is quite new. So I hope I will do a reasonable job to actually overview where we are today. But I always like to start my talk looking exactly at our own Milky Way, where we can look at star formation in our own disk at the highest physical scales. And here, for those who are used to, you see our map in the radio millimeter, where we see essentially where in this dense core are massive stars forming. And actually, this is Cygnus X, and this plus indicates already the O stars. They are producing feedback and actually acting on the molecular clouds where the star clusters are forming. If we wait long enough and we look in our own Milky Way, we see this sequence. We see stars from the star cluster recently forming. Thanks to their feedback, they are removing the leftover gas of the molecular clouds. And there is an entire field of astrophysics actually studying this process. And then if we wait a few 100 million years, we see that this star cluster continue living in our own Milky Way disk in a kind of a bound, semi-bound gravitational state, possibly surviving a few 100 million years. But we are also seeing relics of things, of star formation episodes, of some history of our Milky Way, of which we still don't understand many things. And these are the globular cluster. So in general, for the rest of the talk, what I'm gonna call young star cluster, even at high redshift, are a compact stellar system with sizes of a few parsec up to 10th of parsec, stellar masses between 10 to the 3 and 10 to the 7. And then we know that they can survive, but actually in the study that we are doing right now, we are not able to provide a model that describes their disruption. So again, when we start to move on and we look inside the most massive star-forming regions, I like this. I think that this is really an iconic way to show what a massive star cluster stellar population looks like. You have a lot of O stars that are providing feedback and also challenging the way we understand how massive stars form. So we see here a tracer of spectra of very massive stars. So these are stars that are above 100 solar masses and that have a spectral feature, in particular the helium-2 in emission, that is really characteristic of very early stars. They show emission line of O stars, but they show the helium in emission, which takes some time if we want to wait for the Wolf-Rayet, where we have seen helium emission always we recognize to be tracer of Wolf-Rayet phases. But so we see these very massive stars, and here we are looking just at our backyard in the Magellanic clouds. And this is relevant when we extrapolate to what we are seeing at high redshift, and we will touch base on this. And then before I move to high redshift, I still like to give kind of an overview of what we understand of star cluster formation in local galaxies, because I think that this it helps us to understand also a bit at high redshift. In particular, we are still debating if in the local universe, star cluster formation efficiency scales with the galaxy properties. So there are different ways. Here you see cluster formation efficiency. Essentially, you can think it as the total mass of stars formed in cluster over the total mass of stars formed in the galaxy over a specific time range, okay? So then this fraction can be very small, and here are typically dwarf galaxies or spiral like M31. They would sit in this area of this region, and here we find the merger system. There is still ongoing debate, which is actually not settled, where there is a trend with star formation rate density. So essentially, where galaxies that can bring in the gas and form their stars in a more compact fashion are possibly able to form more of their stars in star cluster. And so essentially, there is a trend, but possibly not. So there is in the literature, you will find both. And I think the Mark Krumbolt's review actually synthesized this debate quite well. And also, about the mass function. So this is a work recently appeared, produced with Gaia D3, looking at the open cluster population in our Milky Way. And essentially what this study concludes is that the cluster mass function of local galaxies, even our own galaxy, can be described by a power law -2. But if we break this down into ranges, then we see that the slope becomes flatter. And the suggestion is that what is happening is that the lower mass cluster are essentially destructing faster than the high mass one, and that's why the mass function flattens. There is something that in this study was not clearly concluded, and is what happens here at the high mass end. But when we have been looking at nearby local galaxies cluster population, what we see is that the maximum mass of the mass function, if we try to describe it as a Schechter truncation, this characteristic mass that you can think to be as the maximum mass seems to scale again with this quantity, the gas surface density in the galaxy, again telling us that the galaxy where they can bring and compress their gas in a higher fashion are actually able to form more massive cluster than galaxies that are typical like our Milky Way disk. This is really important because now that we move to high redshift, we see evolution in the galaxy properties, and actually I think what we are seeing, it reflects in the cluster population. So it can tell us something about the condition where a globular cluster formed. So, and then here up define the globular cluster demographics. I think this is also an iconic plot. Here we are looking at the age of the globular cluster versus their iron abundance. And what we see for the Milky Way is essentially that what we think is happening, that these are globular cluster that formed in our Milky Way progenitor, while the sequence that we see here are a globular cluster accreted from the dwarfs that the Milky Way progenitor has been merging with. When we look at the globular cluster, we see also chemical pattern that we actually still don't understand where they come from, and they are connected to the CNO cycle of elements, and essentially they are called the anti-correlation or correlation. For instance, in sodium and nitrogen, we see a clear correlation with the spread of the red giant branch of globular cluster. We see then anti-correlation in sodium and nitrogen versus oxygen, telling us that the physics that essentially deplete oxygen while increase the nitrogen and the sodium, the polluters, cannot be anything taking place because iron is not changing significantly in the stellar population of a globular cluster. This is really intriguing also if is put in the context of the ages of the globular cluster and their masses and where we see the multiple population or not. So this enriched sequence of stellar population. And it seems that we are still not able to trace multiple population on globular cluster that are actually younger than roughly 2 gigayear or they formed in the Milky Way or Magellanic clouds at the ratio is 0.6 and below. This can be totally, so it's not even this age limit understood if it's due to stellar evolution because the multiple population are found in evolved stars or is a physical limit. The something is different after that redshift in the way the star cluster formed. And finally, another piece of the puzzle, which will become clear then towards the end of the talk, is the fact that we start to find evidence for intermediate mass black holes. This is actually omega Cen, so it's not really a globular cluster in the sense of a single star cluster that formed that has evolved and about time. Omega Cen is thought to be a nuclear star cluster, but still the evidence that an intermediate mass black hole is in this structure is quite telling also for the high redshift and relevant. So in the first part of my talk, I will start to unravel galaxies. And to do that, we are going to look at different approaches. And the first way we have tried to understand the structure, the way galaxies at high redshift form their stars, has been, for instance, these are a seminal work produced by the Elmegreens in the 2000s, and then followed up as we got deeper and deeper observation from the Hubble Space Telescope. We could clearly see the morphology of galaxies are evolving as we move to higher redshift, and here we are reaching essentially cosmic noon. And then the light of these little blobs here, it cannot be compared to any giant star-forming region. If you take 30-door giant star-forming region and you put it at redshift 2, it won't look so luminous. There is a lot more mass in these regions than what we can think to be in giant star-forming region in local galaxies. So we are looking essentially at different mode of forming stars. Morphologies of galaxies are changing. These stellar clumps appear, dominate the UV light, so they are actually young structure. And what people at the time thought is that essentially these are gas-rich disks where fragmentation is taking place on disks that are therefore thick. So the size of these clumps will correspond to the thickness of these disks. And therefore, this is all this scenario called the violent fragmentation. So the fragmentation will take place not in the giant molecular clouds, but actually over the disk scale of the galaxy. Essentially now with JWST, this picture is actually evolving. And what we see is that galaxy galaxy morphologies are actually not changing so rapidly. Beyond the cosmic noon, now we see with James Webb that actually we find these galaxies up to redshift 6 and even larger. So in this study, it's redshift 6, but we see the fraction still keeping constant up to redshift 7. And we see bulge and bars actually in the morphologies of galaxy beyond the cosmic noon, so up to redshift 3 and 4. So it's like this is opening all a new way of actually seeing how galaxies are evolving. And the clumpy fraction, so what is the stellar light in these galaxies produced by the stellar clumps that I just showed, is actually much higher than previously thought. So this is what was pre-JWST studies. And now here you see the JWST one, because with JWST we are more sensitive and we are resolving the light of galaxies. So we see clumpy fractions actually to be higher than previously thought. This is really important because then when we use lensing, what we are doing is we are taking a foreground galaxy, we put a magnifying lens, which is a galaxy cluster dark matter mass, that is bending the light of the galaxy and at the same time is magnifying it. So we can actually see resolved galaxy into their structure. And therefore, we move from a picture where we see this fuzzy emission into something that starts to break down. So here you see a galaxy lensed by a galaxy cluster. And this is a very low magnification. So here the magnification factor is 2, while in this figure here it's the same galaxy, but with the magnification 5. And we see that a clump that we thought to be a single structure in these high-redshift galaxies actually break down in multiple objects and smaller scale objects. So then we are moving into a framework where if this is the field resolution, all the clumps that we detect in galaxy are becoming smaller and smaller. And these are already with JWST, with the HST, we know that this was possible. And also the masses, we move from masses that reach almost 10 to the 10 into peak masses that go around 10 to the 7, so 2 orders of magnitude smaller. But this is good. It means that we are actually resolving these stellar clumps, and within them, we are gonna find the star cluster. So in the study, in the first result that I would like to show you, simply to give you the context of, okay, we will not manage to resolve all the galaxy down to parsec scale. The majority we manage to resolve down to hundreds, but even studying the clumps' physical properties are important to understand what happens to the cluster population that are forming within these clumps. So in this study done on a Bell 2744 galaxy cluster region, this was the first region that James Webb has observed essentially with all NIRCam filters. So we have a suite of 20 bands to do analysis of clumps within galaxies. This is an overview of this beautiful field that we have been studying. So what we find essentially is galaxies were become increasingly lose their appearance of regular disks as you go and move to higher and higher redshift. But at the same time, you see that their light continues to be dominated by clumps. So 40% of the galaxies have spectroscopic redshift we have studied. But actually, when we move a redshift above 5, we have 70% of them with confirmed spectroscopic redshift. And this is because we are using what people who study this field to do galaxy studies, so they are focusing mostly at very high redshift, and therefore this is the byproduct. We have actually better redshift estimates at higher redshift than low, but it doesn't matter because essentially with the 20 bands, we can derive redshift with the same precision as with the low resolution spectroscopy. So in this first plot here, we are plotting the mass of the clumps versus the mass of the galaxy. And we are color coding this as the age of the clumps. And what we see is essentially that as we move to more massive galaxies, clumps are not anymore the dominating stellar structure in their galaxy disk. So we are seeing essentially an evolution in the way galaxies are forming clustered star formation. Galaxies that are low mass, they have this very dense concentrated structure. They are also very young, while galaxies that are increasing in their mass, stellar clumps seems to be older. So probably they were produced in a past event, star formation event, and then they are now evolving in a disk that is evolving on its own. We also see that the stellar surface density of these stellar clumps are really high. So for comparison, here we break down the stellar clumps, stellar surface density as a function of redshift. And you see a bit of a trend, and this trend is here are the completeness limit. Essentially, we don't see clumps that are faint at higher redshift, but at the high mass, at the high surface density range, we are complete. So we are detecting all the structure. And we clearly see, so this is the dotted line, is the typical density of a star cluster, a young star cluster in the universe, Well, this is the average density of a globular cluster. And we are talking of structure that have between 50 and 100 parsec in size, have stellar density already comparable to globular cluster. And to me, this is always quite amazing. We don't see anything like this in the local universe. And of course, what we see also is as we move to higher redshift, we are seeing the clumps actually having higher star formation rate densities, surface densities. So essentially, for same physical area, clumps at high redshift are forming more stars per unit area. And this is also very important. They are younger, they are forming more stars. So the mass function of these clumps, and again, we are here within 150 parsec, is a bit flatter than -2, but actually you should think that this flattening is probably due to the fact we are not resolving the units. The stellar units, there are still blends of star cluster, and the blending actually makes the effect, it flattens the mass function. This, we have run a simulation for this, so it's easy to show. But what we concluded in our studies that the slope is compatible with -2. So these clumps are forming out of fragmentation within their galaxies. And of course, as we move to cosmic noon, we see that the clumps can become actually very massive, while clumps forming in galaxies at increasingly higher redshift, they can reach, so these are very low numbers, but they can be massive, but not as massive as we see in the cosmic noon system. So now in the last less than half 20 minutes or so, I will focus on star cluster. And actually the question that we are trying to answer is when and where did the first star cluster form? So to answer this question, I think I will start from simulation. I know that you have a floor talking on Monday, and I have not included many slides about simulation, but I like this work from Valenzuela, where essentially he collected all the simulation that until he produced his own had looked at star cluster formation in a cosmological setting. So different simulation make different assumptions on how star cluster form. And what he did then, he compared other different run from same simulation, or like sometimes it's one simulation, with the observed distribution of the age of globular cluster in the Milky Way. And what he concluded is essentially that the Milky Way globular cluster formed around the redshift 12, 13, but actually the distribution is quite broad. So we can't really say when the first globular cluster formed. And we can make this, we can look at this in a different way and say the high redshift star cluster that we are seeing forming a redshift 8, 10, are they likely to become a globular cluster around a Milky Way-like structure? And it seems to be that, so in simulation, especially simulation that try to form the Milky Way at redshift 0, star cluster formation starts a bit later than we are actually seeing. And so is this a problem of simulating low dark matter mass halos, or is this a problem that the prescription we are using to form star cluster really doesn't reflect what we are now gathering from the observation? This is an open question and I don't have an answer. But we can look at what is happening in the galaxies at high redshift. And now we are moving from a situation where, so pre-JWST, we had just a few tenths of galaxies we knew above redshift 6, where we knew the redshift spectroscopically, and we could infer some physical properties from spectra, to entire another opening an entire new parameter space of very high redshift galaxies for which we can also gather spectra and derive physical properties. And for instance, in this collection here, we are simply showing that as we look at higher and higher redshift, the galaxy seems to be more luminous than we expected, and thus open a broad range of questions to whether are galaxy forming stars more efficiently, what is essentially causing this excess in luminosity that we didn't expect before James Webb. We also know that galaxies seem to form stars at very high redshift. So we are here at redshift reionization era galaxies. They form stars in bursty phases. And essentially, if we look at the very luminous one, they have all very high equivalent width in O3H beta. This is telling essentially that they are really effective at producing ionizing continuum photons, while galaxies that are in the intermediate range luminosity, low range luminosity, have a broader equivalent width. So this is start to be a mix of galaxies that probably are bursty and very faint, so very low mass galaxies, or they are post-burst galaxies, so galaxies that have passed their peak and now occupy this range of distribution. And then another final property that I also like to put into context is the size of galaxies. As we move to higher and higher redshift, so we see this is from redshift 2 and then up to redshift 7, and now we are moving to redshift 14. Galaxies are becoming extremely compact. And in fact, if you would essentially estimate this, these are ranges of just 100 to 100 parsec in sizes. So we are looking really at very compact galaxies. There is also something very interesting, and I think that this is interest also for this audience, is about the enhancement in nitrogen. And I like also always to use this overview from G et al. And I invite you, if you are interested in the topic, to use this just to dig up all the references. There is now many groups are looking into this nitrogen enhancement. Here you see the galaxies that look enhanced in nitrogen when we look at their spectroscopy are especially more compact than the average galaxies. And when we look at their nitrogen over oxygen abundances and we compare it with the objects that we are more used to, for instance, the circles here are showing the H2 region in dwarf galaxies, and while this violet are the median distribution of metallicity of nitrogen over oxygen abundance in field stars. Essentially, what we see is that the majority of galaxies with enhanced nitrogen emission are sitting in a region that doesn't really overlap with what we consider a normal nitrogen abundance for a given oxygen abundance. It is also important to notice that all these measurements have been done in the UV, and emission carbon and so carbon nitrogen line emission in the UV are produced by very high density electron density gas. If you, for the same galaxy, for the few where one can cover the optical spectrum and find the nitrogen emission in the optical lines and also oxygen. Essentially, what they see is that if you use a low density tracer, it seems that this excess to disappear. But so there is this caveat that we actually don't know if this trend is real or is driven by this effect, because we are looking in the UV and so on. But it has now been confirmed for about 20 galaxies. And what you see here, that these abundances we are seeing doesn't really overlap with the stars, the first generation stars of globular cluster, but more in line with what we call the second generation, or the one that shows the anti-correlation in nitrogen, sodium, and oxygen, as I described at the beginning. So this is really very interesting. And essentially, people working on galaxy scale are all pointing fingers at these very massive stars producing this anticorrelation, are AGNs, are AGB stars. It's all going on, the debate, very massive stars, supermassive stars, and so on. It's quite exciting, actually, to follow the field. But coming back to star cluster and actually direct evidence of detecting star cluster. So if we look at the cosmic history, I think that the record breaker is now the Misty Moon. It appeared last week. So we see a galaxy magnified by roughly 20 times, where we see this compact structure. In particular, this is roughly 10 to 20 parsec in size, this bright system here. So we are looking at a nuclear star cluster formed with some smaller objects surrounding and breaking down in a galaxy redshift between 11 and 12. This is another arc which is broken down into 3 little systems with sizes compatible with being star cluster. This is, of course, the example close to my heart, the cosmic gems, where this 5-star cluster really appeared. Within 50 parsec, you see 5-star cluster of 10 to the 6 solar masses at redshift 10. And then it's not the end. We see star cluster every time lensing is able to magnify the light of the galaxies. So this is the Far galaxy, a redshift 8, the sunrise arc, all star cluster, and so on. And what is coming up is actually that we don't see simply them forming or being then tens of million years old in their host galaxy. They seem to survive, and they seem to be already in place, like a globular cluster in the Milky Way. But now we are looking at cosmic known galaxies. So this is all really exciting. And for today, to conclude, I've tried to gather all the results of what we understand of this high-redshift star cluster. I will not be able to go through each work on its own. And to do that, I will use GLIMPSE. So GLIMPSE is it's a cycle 2 JWST large program. It's the field AS1063. It's one of the frontier fields, so it has a very deep Hubble observation. And now it has the deepest JWST observation performed in a lens cluster. It is so deep that essentially we can really see all the little tiny structure within the arcs, and we can detect with the reliable measurement the star cluster at the redshift between 1 and 10. And in fact, you see the V-band restframe of all the cluster we have detected in different galaxies, and as a function of the size that we recover. So here we are looking at all this little circled system are a system for which we have an upper limit on the size. So they may be smaller than 10 parsec. And here you see for the study, the result I'm gonna show, we put a cut at 20 parsec to make sure that the light we are measuring is really dominated by the star cluster within them. But these are the Hubble field where we didn't get really very high magnification system, and how GLIMPSE going really deep has allowed us to reach single star cluster to detect a single star cluster. So we also included the objects from the literature. I already presented some of this structure. Essentially what we did is we now analyzed all the photometry in the same way. So we removed the bias of using different SED fitting codes, which is also a caveat when you compile things from the literature, because some people assume non-constrained star formation history to measure the star cluster stellar mass, and then you get the very high masses and old ages for systems that probably are just a few tens of million years. So, but we applied the same methodology to everything so that we don't include the biases from using different methods. And essentially the red shows the distribution of the population we consider star cluster. And you see those are the ones that reach the highest magnification. So we look at system up to 100 times more magnified. And of course their sizes, we apply the kata 20, but you see it peaks around 10 parsec. The redshift distribution of clumps and cluster is the same. The masses are slightly smaller, and so are the luminosity, of course, because we are resolving into smaller structure. And we also notice as we go to smaller structure, we are moving into higher stellar surface density and star formation ray surface density. So when did they form this star cluster? We are color-coding this object at the time when we observe. So we observe them, for instance, around the cosmic noon. But the ages we derive for this object are actually quite old, or can be as old as redshift 10, 12. And this is in line with the fact that we expect, and we are seeing now when we resolve galaxy at redshift 10, 12, that they have a star cluster within them. The number density, of course, is larger around the cosmic noon, and we know and we expect that there the population we see at redshift 0 has formed the bulk around the cosmic noon. It's a matter of survival time scale, most likely. Then we see their stellar densities. So this is an initial plot from just last year, 2024, where we're looking at the cosmic gems, and we derive a stellar density of 10 to the 5 to 10 to the 6. And to put into context, if we would plot here the nuclear star cluster, this is where the stellar density are of nuclear star cluster redshift 0. This is what a galaxy redshift 8 stellar surface density typically is. So you see that a galaxy redshift 8 is as dense as the local young star cluster we see in the universe. And then clumps are around 10 to the 3 solar masses. So we think that this measurement may be real. So this was in 2024. We argued that essentially you expect a globular cluster to form dense and then evolve into this range. So this is the blue cyan contours, because they essentially will expand. They will lose mass due to stellar evolution. They will lose mass via relaxation, and also stellar black holes and N-body interaction will make such that the star cluster will relax and lose mass. So it's not completely strange that actually we see the young star cluster at high redshift to be denser than the globular cluster redshift 0. But now you see here, essentially, if we include all the glimpse objects, and many of them you see have upper limits, this is how an upper limit will move object. So if you have an object of 10 to the 6 solar masses with upper limit in size, then the density will become higher and higher as you resolve their sizes. So we see essentially that we are reaching already the sizes of globular cluster, star cluster, and still the density remains quite high. And of course, it's an effect of, it's a bias due to the magnification. We need the really high magnification to resolve star cluster at high redshift. And when you have a lower magnification, then you are down here, but still very high high density structure we are looking at. And then one thing we can do is essentially to look at are they gravitationally bound? And of course, we cannot look at the dynamics of the kinematics of stars within this object, but we can make some simple assumption. So we can look at the crossing time because we know the size and we got the mass. And we know also the age of the system. And if the age is longer than the crossing time, then we expect that this structure to be gravitationally bound. And when we apply this criterion to the sample that we have collected, we see essentially that the majority of them, like 99% of this system, are actually gravitationally bound. So this pi factor is significantly larger than 1 in most of them. So this is really interesting, and I'm now wrapping up. I see that I'm at the top of the hour, but at this stellar density, runaway collision are probably the order of the day time scales. So it's obvious that this star cluster at high redshift probably harbor very massive stars, and we see them. So in this study, for instance, the line ratio suggests that there are a very hot stellar system within them. And then another way channel is, of course, via merger, we can reach this supermassive star with masses above 10,000 solar masses. And we can also explain via the typical evolution of massive stars, the enhancement that we are observing, a different channel for this enrichment in nitrogen with respect to oxygen. And finally, we expect intermediate mass black hole to grow within them. And this has already been, it was in the 2000 a topic that was investigated, and now has also gained the momentum back again. Essentially, if we look at the very high redshift, we can start to populate what seeds create the supermassive black hole that we see in the center of galaxy at lower mass. And essentially, we expect there are different routes, so POP3 stellar seeds, but also nuclear star cluster become an important channel to form intermediate mass black hole. And what we think is that the fact that we see the star cluster to be so dense at high redshift indeed so it gives this channel more credibility to form the seeds for the supermassive black hole to form and grow, actually. And in fact, now there are several simulations. So this is a work recently published by Rantala and collaborators, where they look at N-body simulation of isolated star cluster, very dense isolated star cluster, very dense. And what they find here, and this was already known, that if a star cluster has very high densities, but doesn't have any primordial binaries, is not able to really form a black hole via runaway collisions, because the collisions become very rare. But when you include N-body and primordial binary fractions, in this case, the binary fraction helps to increase the rate of black hole mergers. And finally, another way to grow this intermediate mass black hole with a very dense star cluster is to actually assume that this star cluster merge, which is not implausible if, like in the cosmic gems, we are seeing 5-star cluster of 10 to the 6 solar masses within 50 parsec. It's plausible to assume that they will merge within them. And if they have formed an intermediate mass black hole and retained them, they can actually, the intermediate mass black hole, merge within them and grow. So in this work, essentially they estimate the type of intermediate mass black hole that can be formed, assuming the stellar density of the star cluster as a function of the stellar density of the star cluster. So I know I'm at the end of the time. Sergio, you should stop me. You know, I can talk for hours, but can I get 2 minutes to wrap up?
Sure. Go
Okay.
ahead.
I wanted to go to the mass fraction, because as we move to higher and higher redshift and galaxies become lower mass, and we find this massive star cluster, there is not really much room to assume that there are a fraction of low mass clusters that are missed For instance, the observed class here, you see this is a compilation from Nakane 2025, and there are all the galaxies for which I showed the star classes, so the cosmic gems, the Firefly galaxy are all compiled here. Essentially, the observed mass in star cluster is already a significant fraction of the galaxy mass. And indeed, Eros Vanzella played this game and say, okay, how much mass can the cosmic gem hide underneath the one that we detect? So are we missing the low mass star cluster? We know the one we observe, and we extrapolate a power law -2. And actually what you see here is that you cannot populate a power law -2 down to 100 solar masses, but you cannot populate a power law -2 even down to 10 to the 4 solar masses. So maybe what we are seeing is that the galaxy, for some reason, because of gas compression, the condition under which star formation is taking place, has made such that has formed just a bunch of massive cluster, but it's not able to populate the cluster mass function because there is not enough mass. Essentially, it was all used up to form this 5-star cluster. So we used GLIMPSE to actually investigate the mass function. We don't have many objects, roughly 60, but we actually could get constraints on parameters. We are not fitting the distribution. We are using posterior analysis, so Bayesian analysis to derive the slopes. And we derive slopes that are compatible with being around -2. We try to understand whether there is a cutoff here again, if there is, but it's so we don't find any cluster more massive. Maybe one cluster is as massive as the cutoff. So we don't really have statistical evidence for a cutoff. And this is my summary. So we see the universe to like to form dense structure, and this is very important. It has important implication when we want to understand, for instance, black hole formation and growth. We want to understand the nitrogen enhancement, all the abundance pattern that we are looking at, and the physical properties that we are seeing when we look at galactic scale, ISM emission, for instance, of unresolved galaxies. And that's it. I will stop here, Sergio. I'm happy to take questions.
Thank you very much, Angela, for this very comprehensive talk and also the very interesting results that you have shown. So before asking the audience if they have questions, I have a couple of very naive questions myself, because this is very far away from the things I do. So the first thing is, how do you determine observationally masses, sizes, and ages of all these galaxies?
Yes, I unfortunately removed the plot with the SCD, but essentially what we do is we extract, I will put back this in. We extract the light, so we fit both the size and the light of each of these objects. When they are very close to each other, we combine, so we fit their size and fluxes simultaneously. And we do that across all the bands for which we have observation. So what we do is SED fitting. So then we try to find the match in the population, in the star cluster population that we create, that reproduces the spectral energy distribution of the object.
Okay, so you assume a given IMF plus the
Yeah,
age, and then
we assume
okay.
the group IMF. Now, the age is a parameter that we fit. We tend to, so we don't fix the metallicity, so we allow the metallicity to vary. Although we know we don't have a strong constraint on metallicity, we use nebular emission when we fit because some of these objects are really young. So we have a cloudy model on top of the stellar population.
Okay,
yeah.
okay. So you are also using this. Okay. And then the second one for allowing Jory to ask, why stars at high redshifts are supposed to be different to the ones in the local universe?
I don't think the stars are different. in the sense that I think that in the local universe it's rare to find very massive stars, for instance, or we have never seen supermassive stars and so on. But as you move to higher redshift and you have a higher stellar density, channel as like runaway collision becomes more viable, sorry, and therefore it's normal to think that you probably have the mass function, the initial mass function, you sample to much higher mass and the 100 solar masses as typically assumed in the local universe, simply because you expect them, they are more massive, so you expect them to form more massive stars within them. So it's a matter of scaling.
Maybe
it's
this
a matter
is a
of scaling. It's not a matter of spatial condition. It's a matter of scaling up. So the physics is the same, but the ingredients are different, and therefore you sample more at higher mass the IMF.
Okay. So it's not necessarily a question of metallicity or density of the environment in this set box.
It is, so the physics of forming stars is there, right? But the conditions are different. So you have a more metal poor environment. You have a higher compression of gas. The universe, so the bar at which star formation takes place is completely different, right? That in local disks in the local universe. So
okay.
I think it's a combination of everything, but I don't think it's so I don't know how to explain my concept. I don't think you should think that you need to reinvent the physics. You need to use the right ingredient with the physics that we know. Yeah.
Okay, thank you very much. So, Jorik?
Yeah, very exciting results, of course, these lensing observations at high redshift. Just on this sort of similar topic, of course, the problem with supermassive stars is it's already very hard to form any massive star. In our own Milky Way, forming massive stars is difficult. Forming very massive stars is even more difficult, and supermassive stars would be almost impossible. And the reason is the strong radiation pressure, not just on dust, but also gas. You get very strong stellar winds that probably set the upper mass limit. So even if the densities are very high and you get lots of collisions, potentially form supermassive stars, these supermassive, they will lose their mass straight away because of strong stellar winds.
Yeah, you are right, Jorik.
My question is really, it's theoretically very hard to make supermassive stars, and we don't have evidence they exist. Very massive stars we know exist. You showed that nice plot from Paul Crowder on the helium-2 emission. We know these exist. So why do we want... Is there any actual observational evidence that we need supermassive stars? That is my question.
Okay, that question. So do we need the supermassive star? I think we want to explain the physical... So we want to explain what we see in the abundance pattern of galaxies. And essentially, there has been observation suggesting that you need a supermassive star, and very massive stars are not enough to explain the abundances that you see.
I don't agree. Which are you talking about?
So this is from Rui Marquez, and in the group of Corinne and Danielle. They made some compilation. And of course, I understand that the supermassive stars model change and their formation seems to... it can be but I agree that we don't have direct evidence of detecting the supermassive star, but that doesn't mean that we can exclude them, right? We are exploring. We are still trying to understand what we see. So, for instance, on the point you made about the stellar winds and how massive. So, in this simulation, they look at the dependency of metallicity, and indeed they see that the mass of the intermediate mass black hole forming from the collapse of this very massive star or a supermassive star they become lower at higher metallicity, because essentially at higher metallicity, the stars lose more material.
Yeah,
So,
but there is the other effect of the gamma-dependent mass loss. So mass loss is not just metallicity dependent. It also depends how close you are to the Eddington limit. So if you're very close to the Eddington limit, and supermassive stars almost certainly are, you don't need to have that many metals to drive a wind. But we have to explore, I agree. I think
I think we are in a situation where we should not left out any and test all, and then I guess it will be the Occam razor, right? What is the easiest explanation? And we are gathering spectroscopy at high redshift, so that is also very helpful, because it looks like this condition in the local universe are not there anymore. So even dwarf galaxy in the local universe do not look anything like the cosmic gems and so on. So we need to be patient. I think there will be a lot happening in the next 5 years, a lot of progress on the way.
Fabrice?
Yeah, you partly answered actually. I was wondering whether, to follow up on what Yuri was saying, if there are prospects for spectroscopic studies of some of these clusters, not just high-redshift galaxies, but specific targets that you would identify in your sample as the most promising to basically unravel the populations that are within these clusters.
Yeah, so indeed there are so some of these objects are very young, and there are spectroscopic campaign ongoing. So for instance, the sunburst arc is like it has a huge amount of spectroscopy even with JWST, and it has a very weird feature, even like Eta Carinae blue, very luminous blue variable feature. So, and the same is for the sunrise and for the firefly. The cosmic gem, we have spectroscopy and it's a post-burst. So we have lost all the ISM tracer in that sense. I would not say that we are in a bad place. We have just started and there is a lot happening. So in the next few years, I'm sure we will get a more stringent constraint on the type of ISM, ionized ISM coupled with the star cluster.
In a related question is you say that you are now in the first step. Is this going to be possible with James Webb? Or what are the perspectives for the ELTs and all these next generation telescopes? What is the observational situation now?
Yeah, so the problem is also, as I mentioned a bit for this nitrogen enhancement, right? So if we look at this plot, sorry, this one, and there is a lot of ongoing study if this nitrogen enhancement is real. So the problem with ELT is that we will get only rest frame UV for a population above redshift 6, right? And therefore we will infer properties from lower redshift, of course, but it will be great. So we will manage to do spectroscopy and go deep. James Webb spectroscopy in that sense has been really revolutionary because it has allowed us to reach the higher redshift. So there is, I think there will be a lot more coming, and there are many studies currently ongoing trying to understand where what we are seeing is simply a denser medium. So the typical ISM of high redshift galaxy is much denser, or we are seeing condition that we don't see in the local universe. So you need the 10 to the 5 to produce this type of pattern. While here is a 10 to the 3 are the lines that produce the electron density 10 to the 3 produce abundance pattern that are normal. So I think we have a lot to learn, and the spectroscopy JWST is providing is definitely, it will be our only chance for the very high redshift. ELT is gonna be transformational, and of course, so there are many of these, not so many here, but simply it's a bias. There are galaxies at lower redshift, like the sunbar star, and there will be many targets that we can go and do spectroscopy of the optical wavelength and solve this issue of density degeneracies.
Okay, any other question by the audience? If not, I have another one with this plot, but let's see if there is anyone. No, so yeah, I was curious because I was also working on H2 region abundances and all this. And then if I understand correctly, you say that there are differences in the diagnostic lines that you are using. So one is UV and the other is optical. So there can be, and there was some works trying to see if for the enriched targets in nitrogen, when you go to optical, then you get lower abundances, and there were some hints that this was happening. But I wonder if it would be possible to do it the other way. So for close by H2 regions, if you get HST observation and you do the abundance analysis with the UV, is that you get higher abundances, or do we have any idea of this? Or?
So yes, so the problem is the H2 regions usually are in this range, right? Between 8 and 8.5. And so these are very low metallicities and abundances. Then the other problem is not all H2 region we sample. I don't know, I have been looking at local galaxy, I never find H2 region with density above 100. I don't know, Sergio, if you ever found the density above 10 to the 3. 10 to the 3, I think it's the maximum I have ever seen. But some galaxy like Class C, those have ISM, so emission line, and they have also nebular emission at the short, in the far UV, and show similar trend, but it's not as strong as you see for this very high redshift. So I think if you find a sample that can be investigated in the local universe in this sense is really useful. And also to get oxygen abundances that are not affected by, if you have a very high electron density, so you start to underpopulate the tracer of density, right? And so on, that we are used. So you need maybe neon as a tracer of abundance in the mid-infrared and so on. So I'm not really an expert in this game, but I know that a lot there is to learn still from the local universe, and we are not there yet. And definitely the redshift has opened this window that we really need to understand what is happening here.
Yeah. Okay. So I'm curious. So I will ask the expert here at the IAC, so César Esteban and Jorge García, to know their opinion on this, and if there are targets that can be of interest for this.
Yeah, definitely. If you find the target, you should follow up them.
Okay, great. So final chance to have questions for Angela. If not, thank you very much again, Angela. It has been great to jump from our common
Thank you all for joining.
Happy to have you here.
Yes.
Ta-ta.
Bye, everyone.
Thank you.